Hello. Thank you very much for coming, and really thanks for the Scholars Association to invite me here today. I'm actually an undergraduate, so I'm probably one of the least educated person here. And as a result, don't expect too much from my talk. And I'm going to talk about very basic probability and measure space. The reason for this talk is because, as you can see, probability is basically everywhere now. No matter whether or not you're doing social science or whatever, you have to touch some sort of statistics. And, but the problem of what really is probability is apparently a problem that only mathematicians sort of do. So I'm trying to address this thing. So first off, I'm going to ask you guys 3 questions and see which is the sensible probability question and what is not a sensible probability question. So throw a die. What is the probability that the sun rises next morning? Does it make any sense? Probably no. Throw a die. What is the probability of getting an even number? Well, it's a sort of a sensible problem, but it's hard to know what the probability is because obviously we are losing some specification. And finally, throw a regular fair-faced die. What is the probability of getting an even number? Then now you can calculate and say, oh, well, it's a half. And so what are the intrinsic differences between these questions? If we can see why these 3 questions, some are completely nonsense and some are very sensible, we will be able to see what, in essence, a probability is. And what I want to try to give you guys an idea is that through understanding the essence of a probability, we'll realize that probability is essentially conceptually not much different from measurement, from length, from volume, from heat. Is actually the same idea. And that's, to me, I think, one of the most profound realization in modern mathematics. So what are the essence of probability? What are the things that we really need to think of? First off, we need something called the state space. So what is the thing that we want to talk about? And these are the things, what are we actually assigning probability to? When we throw a die, we are saying that we want to assign probability to the possible numbers or the values on the die. We're not assigning a probability to whether or not the sun is going to rise tomorrow. And that is why, under the first question that we just asked, it makes completely no sense. And on top of the state space of having what we know is the thing that we want to assign with, we also need to consider what we call as event space. Now, this might look very trivial to you because once we specialize what the state space is, then we can easily define the event space as in any combination of the state space. So the event of having an even number is essentially the same as getting a 2, getting a 4, and getting a 6. And so it seems intuitive to say that if we have the state space, then effectively the so-called event space are the combinations of the state space that we have. Now this is a pretty nice idea and a very fundamental approach of probability space, but that is not necessarily true if we have some very weird thing. So for example, if we are looking at a state space of something if we consider our state space to be points on a dartboard, and we are talking about throwing darts into a dartboard, then you will realize there's something called uncountability in terms of the different sizes of infinity, would mean that an event space is not as trivial as we think it is. But that is something that I'm not going to cover today. And finally, what essentially is important is a probability measure, because we need to tell how likely the event is, or how likely I get a 1, 2, 3, 4, 5, 6. And that is the problem of the second question just now, because we didn't really specify what state value we have, and we didn't say whether or not the die is fair. And by having that problem, we will essentially know that 1 is completely a absurd problem, because sun rises next morning. This is not in the event space. So it is not something that we can talk about top probability with. And on the other hand, if we throw a die and see what is the probability of getting an even number, we don't really know about the state space because I didn't say if the die is 20-phased or 6-phased, right? So I don't really know how to describe this sort of probability. But if we have a regular 6-phase die, then it's easy. We know that the state space, the stuff that we have, is 1, 2, 3, 4, 5, 6. We know that this is just a fancy way of writing all the combinations of possible of this number. So 1, 3, 4, 1, 4, 6, etc. These are the combinations. And finally, we also have that each of the probability is 1/6. So how can we calculate it? Well, easy. You just say probability even, and you ask what does being even means. Then you realize that it's actually just a composition of the original state space 2, 4, 6, and then you do the addition. Now, this is very interesting. This is not this seems trivial to us, but this is actually, in a sense, an integration. So I will now jump into a completely different thing called a measure space. So around early 19th century, if not mistaken, Lebesgue, a French mathematician, he was thinking of something very philosophical. And he was trying to ask a generalization of length and area. So one thing that we know is, say, this line from 0 to 1 is of length 1, let's say. So naturally, we say, well, if I take away 1 point out of this line, what is the intuitive length of this line? Well, it should be still 1, right? Because you just take away 1 point. It doesn't really affect the length. We know, mathematically speaking, 1 point is infinitesimally small. So what about we take like finitely many points? Okay, does that gives us the same length? Yeah, it should be intuitively. We think that that should gives you 1. Now, okay, now, but you know, what if we take away infinitely many points? In particular, we take away from 0 to 1, we take away all the rational points. So if it is a rational number, we take away it. So we know there are infinitely many rational points in 0 to 1. But the interesting thing is, taking away these things actually won't affect the line. It's an argument by Cantor back in 19th century, which says that essentially, if you take a countably infinite subset out of this 0 and 1, taking it out still gives you some sort of length 1. Now, this is called the Cantor set, and it's very interesting. How do you construct this set? You originally have a 0 to 1. You take away you cut into 3. You take away the middle one, and then you're left into the two pieces. And then again, you reiterate this process, and you get 4 smaller pieces. And you will see essentially that these intervals get smaller and smaller. Now, if we do this infinitely many times, the intuitive answer is to think that this thing should go to 0. It shouldn't have any length, right? Because obviously it's just getting smaller and smaller. But there are actually infinitely many points that are left behind after this process. Actually, uncountably infinitely many points. It's just a huge amount of points. But we have things like that that gives you measure 0, which means you have something that has infinitely many stuff, but with measure 0, with length 0. So if you look back to measure theory, and we look at anything that we can assign measure with, it's just the same thing with what we just taught about probability, because we need to have something to ask, what is the sample space? For example, in just now, we have 0 to 1. That is the thing that we want to look at. What are the things that we want to assign this measure called length in? And in geometric objects, we have surface, real line. Abstract concepts, we have something called probability events. And then we ask ourselves a collection of measurable sets, which here we would say, for probability, what are the events here? Or in a real line, what Lebesgue realized that you can specify a specific class of sets inside a specific classes of sets inside the line just now that we can give what we call as a length. And finally, we have a measure function M. And And I'm not sure. I shall stop here and see if you guys have any questions. And if you guys want, I can continue into something that I think is more amazing. So, is there any questions so far?
Nothing right now.
Okay, good. Okay, so now we go to a completely different problem that links with measure theory very well and the understanding of expectation and very fundamental concepts in mathematics. So, if I asked you to count a pile of coins in front of you, and that these coins have value $1, $2, and $5, how will you count? How will you find the total sum? And just loads of coins here, okay? How do you do that? There are two ways of actually finding this sum. First, well, you pick your first coin, and you look at, oh, it's $2, so you write 2. Oh, my next coin, oh, there are $1, and oh, $5, and then you sum, and you just sum all of them. This is essentially, you take the sum of the value of your nth coin. This is a way of taking a sum, right? But there is another way that is more intuitive. Well, you ask yourself, how many $1 coins are there? How many? How many $5 coins are there? How many $2 coins are there? And then you count how many of them. You times 2. How many $5 times 5? How many $1 times 1? Get that number and sum them up. Now, this is called the Lebesgue integral. And this how many is essentially a measure. And this gives us a really good understanding of something that we need to sum. Because here, we sum the first thing, we sum the second thing. But in probability, say for example, a Brownian process, a random motion of a particle, and you want to ask yourself, what is the expected value of that particle at time t? So 10 minutes later, where will it be? How can you find, oh, what is the first infinitesimally small time moment, and what is its possible trajectory, and then you go and you do the sum here? It's impossible. But you can ask yourself, well, what is the position there, and what is the probability of it being there? And then you can do this sort of a sum, and essentially you get an expectation. So expectation, or what we so call as average in general, is just a very, very simple concept. You ask yourself, sum, what is the probability of something, and of an event we call omega, and what is the value that we want to understand that depends on the omega? And you do the sum. And this is completely what we so call a Lebesgue integral. And the Lebesgue integral connects very well with the measure theoretic and this generalization of integration theory called Lebesgue integration theory, which gives us a very axiomatic and intuitive approach of what probability is. So now when you want to study like a very complex situation of, say, Brownian motion, or say some sort of a weighting process, all you need to care about is to ask yourself, what is the probability measure? What is the thing that we are measuring? And by constantly asking ourselves, what really constitutes a measure space? What really constitutes a measure? What is the essence of it? We will be able to do very complicated things like expectation, variance, or very complicated process just by understanding what are the essence of what we call the sample space, the measure space, and the measure function. And this is what, to me, I find the most interesting part of probability theory. And it's also why, to truly understand probability theory, we need to understand what we are doing when we are trying to measure something. That's